So the next team is team 34. You can start.
Okay. Good afternoon, everybody. We are Team 34. My name is Paulo.
I'm Thomas.
James. I'm Armand.
And I'm Ethan.
And we'd like to present the engineering design and manufacturing process of a foldable scooter. So, next slide, please.
No?
Yep. There you go. So we'll start with a quick, little presentation outline. First, we'll start with a process overview, followed by basically relevant calculations and forces we need to find to kind of inform our design, followed with actually how did we manufacture this, and completed with the full build and concluded them following parts. Okay, so product overview. Our client is Sylvester, and he is an aviation hobbyist who owns a semi-SXT motor glider. Basically, what we learned is that he travels to local towns in the New England area, kind of just have fun at a glider. Come on. However, issues is that the local towns are inaccessible from the local airfields. This is commonly described as the last mile problem, as you might see in supply chain manufacturing. Basically, the idea is that from point A to point B, very easy to get to that, but from point B to point C, even though it might be less than a mile or even 2 miles, it's kind of hard to travel that area without the right mode of transportation. This can be solved with a manual push scooter. However, currently in the market, there isn't any scooters that are available that meets the requirements and specifications Sylvester is asking for.
So during our primary review with Professor Sylvester, we determined that the variable rider height would be between 5 to 6 feet, or between 1.55 meters and 1.85 meters. We also understood that the compartment dimensions were going to be 30 foot 15 inches by 8 foot 25 inches by 11 foot 25 inches. This already gave us our overall size constraint for the maximum size of the scooter and its building position. It also has an aperture of 16.25 inches and 6.5 inches, which gave us the third dimension as to what our scooter could physically be within the constraints of. We also, from our client interview, needed a simple actuation mechanism, nothing that was too complex, something that could basically be activated within 2 to 3 seconds with minimal effort. We also understood that he preferred a front handheld brake as opposed to a rear-based foot activated brake, and it needs to be suitable for rides of at least 2 miles, which is the average duration of the trip from the airport to the surrounding areas. We also took into consideration that the average rider would be about 200 pounds or 90 kilograms, which is another reason why our scooter had to be more custom designed, because any scooter that was on the market that did have the size variability was not actually able to hold an adult rider. They were all basically designed for children, so we had to design one that was much more sturdy than what the market currently had. And the scooter itself had a 44 pounds limit technically, because that is what the overall compartment was able to hold, but realistically we wanted to then hold about 11 pounds total. And after our optimization processes, we were able to get that down. As for kinetic analysis, when we were first designing the scooter, we needed to understand the forces that were going to be acting on the body as a whole. So we took into consideration the overall body forces, as well as the forces that each individual subsystem would be experiencing, such as the deck, the uprights, the folding actuation mechanism, and the handlebars themselves, which informed design choices as to what materials to select, and the machining processes and the joining mechanisms.
So combining our earlier material selection research needed for weight and strength requirements, as well as I think you jumped to say.
Yeah, sorry. So as you can see here, this is the forward view of the CAD, front, side, top, and ISO. So as you can see here, all of the different dimensional analysis that we previously mentioned, as well as the specifications were taken into account. You can see that there is definitely an aviation aesthetic influence in it, including the hexagonal pattern, which is common in different airframe structures. And then the deck design is from a symmetrical airfoil, just to lend back to the roots of what the purpose is. We have the different mechanisms, as you can see right here, the folding mechanism subsystem, which will be touched in depth later, and as well as a telescoping upright, which allows the dimensional constraints to be within the compartment dimensions, as opposed to the full open configuration shown here. And as you can see right here, this is how it folds. This is just a CAD of it. Later we will show it actually folding, but it's simple. We have folding handlebars, which Paolo will delve into later, a telescoping upright, and the folding mechanism that folds at the fin, which you can see in the fifth image all the way on the right.
Yeah, so combining our earlier material selection research needed for our weight and strength purposes, as well as market research, we came up with the following selections. Our total cost fell within the $500 budget, and there's room for extra parts that are needed. So in terms of designing the deck, we took inspiration, like Ethan mentioned, from the aircraft design. So the actual outer body of the outer shape of the deck is, like Ethan mentioned, a reflected airfoil. So we took that inspiration from the actual cross section of the wing, and then reflected that so we get a kind of nice uniform shape. And then additionally, the hexagonal components. So we used hexagonal pockets underneath to really like reduce the weight, and then also put some of them all the way through so that it kind of gives that aesthetic as well. And then we made sure to keep the standing area large enough for a size 17 US shoe. So that really gives it accessible to a wide range of riders. And then finally, our bonus feature was that we made this deck kind of modular. So we have a support system underneath the deck that you can just attach a deck to. So you can kind of design your own deck and build that feature right in. And as you can see here, we have two different deck designs. So those are the two that we designed for the project. And then we manufactured one of them. It happened to be the lighter one, just so that we can get a nice finished product. So then in terms of machining it, for the deck, we used two different machining processes. The first one was the bottom side. So machined out all those pockets underneath the deck, as you can see in there. And then we did half of the outer contour. So we went half the depth of the aluminum sheet. That way we can still clamp it when we flip it over and attach it to the actual CNC machine. And then the second operation, we kind of finished that pass, so went all the way through and essentially released it from that stock block of aluminum. And then after that, we had a couple of clearance cuts to make so that it fits in with the actual rest of the assembly. And those were done on a manual mill so that we can get that nice precision. And then in terms of the wheels, we once again took a lot of inspiration from the STEM S6 motor glider. So the wheels, we looked into a couple of different options in terms of spokes versus a kind of negative hub that you can see we ended up deciding to go with. And the shape of those cutouts are actually the exact same shape of the STEM S6 motor glider propeller. So we took an image of that and then traced that sketch and cut it out there. And then finally, we wanted to reduce the weight as much as possible. So we used some FEA through SolidWorks to lighten that up. So we essentially put 10,000 newtons of force on those wheels, which is way over what we really needed. But we wanted to make sure that we had a significant factor of safety. And essentially that's like, you'd think it's larger than kind of just a person riding on it. And we wanted to make sure that we account for if the rider goes off of a curb and kind of drops down. We made sure to account for that within the tire compression and just calculated that force needed to withstand that impact. And overall, we ended up lightening our wheels by about half and kind of thinning that inner hub to about 2 millimeters. And then once again, for manufacturing this, we did 2 CNC operations. So the first side, we cut out that hub and again, halfway through the outer contour, flipped it over and did the same thing. Then put it on a lathe, and to ensure that there were some press fit dimensions, which we put the bearings into on either side so that it rolls smoothly. We put that on the lathe to get really accurate with those dimensions. And then finally, we grooved out a channel on the outer edge to fit the tire so that we can just press that in and kind of really seal it in there. The tires were 3D printed out of TPU, and we used a gyroid infill, which we chose because it's isotropic properties, which means that essentially its geometric and structural properties are the same no matter what orientation you put it in. And we designed it like this so that we can modify the infill percentage. And the infill percentage is essentially how dense that tire is. Because it's an airless tire, we wanted to make sure that we get the correct compression to account for that 10,000 Newton force that we put down on it. So, yeah.
Yeah, so the next subsystem to talk about is the folding mechanism. So the defined folding mechanism in this part was just the total system that connects the deck assembly to the upright and front wheel. So as shown in the image to the left, it includes the main arm component as well as the headset bearings and the fork to the front wheel. So the arm was designed with the dimensional analysis taken in mind so that it reduces the total fold configuration outer dimensions while not reducing any dimensions of the scooter open configuration. And another part of the arm design was keeping the hexagonal pattern continuous through it, just to have a uniform aesthetic through it. And as you can see right here, we went through a couple of different designs and all of them tried to keep the structural stability as much as possible while keeping the aesthetic. And the actuation method for it is just a simple button built into it. Just press it, you hold the pin. And so we did not have enough time to complete the manufacturing of the intended 6061 aluminum component of this. The way we would do that is through a combination of different manual milling and CNC milling operations. However, what we were able to do was create one-to-one models of the piece from PLA FDM prints. And shown here is just a slicer of one of the parts that ended up on the scooter. And even though it's not the original metal material, it gives us a complete assembly just to show the functionality of it.
So on the handlebars and uprights, so based on the engineering specifications, we know that the compartment has a max width of 6.5 inches, meaning that if you want to fit a scooter inside, in order to have also a handlebar, a classical component has to be considered as well. So we decided to do a simple folding mechanism that uses a pin lock to lock in place. And same thing for the upright, we just use standard tubing diameters as seen in market research on basically what typical size like uprights are. So this assembly is made out of entirely 66-1 aluminum tube stock and 66 aluminum like mount stock. For the manufacturing components, it uses a lot of mainly facilities use of Epic. So that includes a CNC mill and lathe, manual mill and lathes, and the hand grips are also made out of the same TPU material mentioned before on the tires. I'd like to emphasize that this entire assembly is manufactured at Epic. So with the machines used, we were able to create type 4 press fit holes on handlebars, and then we were also able to create slot clearances up to 10,000 inches size.
Yeah, so as you can see in the images up here and right here, this is the complete assembly of the scooter. So all of the different assemblies that were done were put together through the combination of the real machined upright wheels and deck and the 3D printed folding mechanism and support structure. And the actuation method, it's simple. It's just remove pins, turn it on to drop the upright, and then press a button to fold. And now it's locked in this configuration. And to open it back up, it's just the same take in reverse, just button, open, knob, up, and there we go. And then sadly, we were not able to get out to the motor glider in time with the final one-to-one model of it, but we did have access, thank you Professor Sylvester, and thank you to STEM for the CAD of the compartment itself. And showing through the CAD right here, it does fit dimensionally. And of course, not shown in this image because this is just a side cross section, the width dimension of the top, thanks to Paolo's collapsible handlebars, is within the 6.5 inches that the opening has.
So in conclusion, we were able to meet the dimension requirements that are design needed. Through CAD analysis and simulations, because it does fit with the synthetic component. And we were well able to maintain a budget under $500 with extra room for more parts, future iterations, which may include for alternative materials. Professor Sylvester offered the idea of using carbon fiber, which is something that did not fall within budget, but with additional funding, we can maybe explore that method.
So, thank you. We'll take any questions.
Have you stood on this?
We have not. So a lot of with the 3D printed parts, we're a little bit afraid of if the 3D printed parts can hold. But we do know that if they were made out of aluminum, it would be able to hold us. And we did the force calculations and the simulations of it. And after the presentation, we're gonna try and ride it and see what happens.
So don't really want to put entire body weight on that when it's already just reflected like that. So
We already know what the volunteer purchase and we're trying to achieve that. I think it's just that unfortunately we can't constraints to.
I'm curious about the button at the bottom, pins at the top. I'm curious about like why not a pin at the bottom or why not buttons at the top. I'm just curious.
The buttons and the voting mechanism, the buttons
Yeah,
for
in the
the.
handlebars. So it's funny. There are a couple of scooters. Razor actually has one where it's a mechanism like this, but there is a pin that you pull out and then push back in. So the reason for something like this was just as a design problem. It was really, really cool to come up with just an ability to just as one piece, assemble it all together, and that's your folding mechanism. So the problem with the pins down there is that's closer to where debris will be hitting and puts right there so something can knock it out. But like Paolo went into for the top, so the pins give a really cool aesthetic on top, and it's where your hands are, so there's good protection. And for further parts of the folding mechanism, we were gonna put a wire so that you can't just pop out and use them.
On the topic of the handlebars, we did look at other, scooters that did create, couple handlebars. And one common method that they did was essentially like plate lock buttons and then just kind of like collapse with some sort of elastic string to kind of thing for over the place. We didn't really want to have that type of actuation. We kind of thought that we'll have flimsy, want to do something more sleek and solid because it is a glider. We don't want it to kind of like move around and like potentially damage the compartments. Also at the same time, spinning lid, every time it's really cold, you really want to try to like hit the spinning gloves with your, big gloves. Something like this, you just have to slide it out, so it's better for multiple like weather conditions.
It was also ideal for the fact that we need to prefer a handbrake as opposed to a rear activated brake. Most handlebars that attach to rear activated brakes, you get rid of the issue of the wire.
Also on the topic of brakes, we use the brake system from Sebastian's current scooter, the scooter, because he taught basically he mentioned that he prefers front brakes or rear brakes, and we figured that since the brake system's already well used, that we could just include that file system. Yes.
Want to do the, what's on there before my question?
Oh, there's no good. I did not know.
Priority.
How did you think that?
Exactly.
Well, you're right about this.
So I mean, we do have the recipient of the scooter in front of us, so we have dimensions that we can work with. But
I'm kind of same height as him too, so like I kind of was like reference.
so we also, for accounting for weight, we just used an absurdly large safety factor, and during our simulations, we just used over the top numbers just to see what would happen under different forces. But for height dimensions, that was actually an issue. So early on in our CAD with the telescopic upright, it worked for me, but not like Paolo or Professor Sebesta. So we had to, of course, I wouldn't know that since it worked for me. But coming together as a group and working with the dimensions that we had, we were able to account for everything too.
And also in terms of materials for design, we opted for 661 aluminum because it's easily machinable. And as I said before, 95, maybe 99% of this project was made in Epic. So basically it was a mix of us learning how to use like machines incorporated with like the staff members, like making sure nothing like gets destroyed. So 661 aluminum is really good at machining, and also current scooters in the market that are kind of marketed towards like adults and like city scooters use 661 aluminum for like the basis of their scooters.
How can you account for a hard brake? So I know you only have a front brake as opposed to a rear brake. How would you account for this, given the possibility of swing torque, rather than having, like a bicycle where it's just like one is like the front and rear in order to like create an equilibrium that doesn't have that.
So yes, so a part of for that is that the Ford design, which show is for a lot of scooters that do have front brakes, it puts the wheel in front of the axis of the upright. So instead of being under, which puts the pivot point under the person, it puts it in front of them. So while that is a possibility under extremely high speeds, the design of the Ford puts in front, and based on the pivot arm, the weight that you're putting back is far enough over that the forces required to tip over would require extreme speeds.
Last question.
So I have two questions for you.
So looking at the folding handlebars, I wonder if you were ever thinking about maybe just doing one pin and not the double pin? Was that a choice?
Yeah, we definitely explored that. However, we wanted to make sure that the handlebar assembly was also symmetrical. On top of that, looking at the previous designs, we came up with different type of body mechanisms. One thing that we considered was also telescopic, so basically a sleeve within a sleeve, so that when you pull it out, it'll try to lock in place. However, like, we didn't think that that would kind of be possible at this time because of the precision and stability that's required to make that type of design. So we opted for two platform handlebar coatings for this design.
Then my second question was, so I'm wondering about the suspension or, any possible aspects to make, the wheels turn in different ways. I'm wondering about, the streets are quite bumpy. How does the scooter navigate that?
Yes, so we're talking with Professor Spesta about the bumpy rides too. The current scooter he has is incredibly large wheels, which can help account for that. But in this design, we didn't have time to do testing for it, but the airless tires and the way we made them with a 3D printer made it so that we were able to interchange the infill. So we could build in suspension into the airless tires, and through more time, we could do suspension testing within the tires without any extra needed subsystems.
Thank you.